Hello everyone, I am pleased to present our work titled 3D Gaussian Splatting for Efficient Retrospective Dynamic Scene Novel View Synthesis with a standardized benchmark. The motivation for this work comes from applications such as sports replay, visual performance capture, immersive broadcasting, and event archival. In these settings, the scene is highly dynamic. The action may be fast, and the interesting viewpoint may not be known in advance. Our goal is retrospective dynamic scene novel view synthesis. Given a dynamic event captured over time, we want to revisit any past temporal instance and render it from a novel camera viewpoint. For example, we may want a novel view at time 0, then another novel view at time 20, and another at time 40. A major line of work extends implicit neural scene representations, such as NERF, to dynamic scenes. These methods model time-varying appearance and geometry by adding temporal information to the representation. For example, some methods use time-conditioned latent codes to capture temporal changes, while others factorize space and time into compact structures, such as Tensor 4D or hexplane. Recent implicit representations have important advantages. They can be compact in memory and often produce excellent image quality. However, they also have limitations for our target setting. They may fail under abrupt motion discontinuities and complex dynamic motion, which are common in sports and performance capture. More importantly, many implicit approaches are not naturally real-time rendering solutions. This creates a gap between high-quality reconstruction and practical retrospective replay, where fast rendering is essential. A second major direction is based on explicit scene representations, especially 3D Gaussian splatting. Instead of representing the scene only through an implicit neural field, 3DGS represents the scene using a large collection of Gaussian primitives with position, opacity, covariance, and view-dependent color. Dynamic 3DGS methods usually extend this idea by tracking, deforming, or applying canonical motion fields to a shared set of Gaussians across time. Examples include 4DGS, dynamic 3D Gaussians, and compression-oriented methods such as Queen. Explicit Gaussian-based representations have a major advantage. They render very fast through rasterization while maintaining high visual quality. This makes them attractive for practical replay and visualization. However, dynamic Gaussian methods also face challenges. Tracking can accumulate errors over time and may break down under large or abrupt motion. Some methods also ideally require accurate 3D point clouds for many timeframes, which can be expensive. This leads to the key question of our work. Can we use per time step 3 DGS more simply and efficiently for synchronized multi-view dynamic scenes? As stated, most dynamic 3D Gaussian splatting, 3DGS methods, rely on temporal coupling. While this works for slow, continuous motion, it creates a penalty in high-speed scenarios such as high compute overhead and significant instability when trying to track rapid, nonlinear athletic movements. Our core insight is that in highly dynamic, multi-view scene such as sports, camera rigs are fully synchronized, calibrated, and rigidly fixed. At any exact time t, the scene is already strongly constrained by multiple viewing angles. If spatial data is absolute, we don't need to calculate how a player moved from t-1. We just need to capture the frozen geometry at t. This is rooted in basic projective geometry. Because we have synchronized multi-view coverage, we have sufficient spatial constraints for high-fidelity rendering at any frozen moment. Adding explicit multi-body temporal constraints is structurally redundant in this environment and often introduces more errors than it solves. Instead of the slow and unstable baseline of training each frame from scratch or using complex deformations, we use warm chain optimization. We initialize the first frame using structure from motion, SfM, to create a Gaussian block, then propagate those optimized parameters linearly across time. A critical part of our method is the no densification lock. Standard 3 DGS allows Gaussian counts to explode over time, moving from 188,000 to nearly 850,000 in just 5 frames. By strictly capping the budget after the initial frame, we achieve 5 times memory savings in just 5 frames, ensuring predictable scaling for sequences of any length. To maximize efficiency further, we use foreground-background separation. We reconstruct the static stadium background, layer A, once with high iterations. For each subsequent frame, we apply multi-view residual masks to isolate the dynamic players, layer B, and optimize only those entities. This drastically reduces the per-frame compute time needed for the final composite render. Let's see the comparison matrix and understand how the proposed warm start 3DGS compares to 4DGS and dnerf. Unlike 4DGS, which has accumulating memory and active densification, we maintain a strictly fixed budget. Our method is specifically designed for the high-speed, synchronized nature of sports broadcasts, where temporal conditioning can be safely disabled after the first frame. In terms of quality, our method labeled as TA3DGS achieves a PSNR of 44.59, drastically outperforming alternatives. Our training speed is highly competitive, and most importantly, our memory footprint remains consistent compared to other approaches. Beyond the algorithm, we identified a major reproducibility bottleneck in the field. Evaluation is often plagued by mismatched camera coordinates, disjointed synchronization, and fragmented export formats. Often, reconciling these dataset formats takes more time than actually evaluating the algorithm itself. To solve this, we developed a standardized Blender API. It enforces a strict world-to-camera standard. This allows researchers to generate training-ready data for any pipeline, whether it's NERV, Instant-N, GP, or 3DGS, automatically and without coordinate ambiguity. This API supports various parameterized capture geometries, including hemisphere, ellipse, and full stadium layouts. These allow for deterministic training and validation splits that are invariant over time, ensuring protocol-level reproducibility across different research sequences. We see our proposed work as a closed-loop complete ecosystem for dynamic scene novel view synthesis. The Blender API generates perfect ground truth spatial constraints, which our warm start 3DGS then ingests. By locking densification and leveraging spatial rigidity, we transition dynamic NVS from custom-made experiments into scalable broadcast infrastructure. In conclusion, the future of retrospective broadcast lies in replacing computational complexity with geometric certainty. By using standardized data and fixed capacity, we unlock the ability to archive, navigate, and render entire dynamic sporting events from infinite viewpoints on a fixed budget. Thank you.